Ever wish you could just like download knowledge straight into your brain?
Wouldn't that be something?
Well, on the deep dive, we do the heavy lifting, digging into the densest research so you don't have to.
Unpacking the big ideas, making them accessible.
Exactly. And today, we're diving into a fascinating lecture, really mind-bending stuff,
Yeah.
by Surya Ganguli.
Let me guess. Stanford professor.
You got it. But it's not just one department. This guy's straddling the worlds of physics,
Okay, getting a picture of the kind of mind we're dealing with here.
neuroscience, and AI all at once. So we're talking about LLMs, those large language models that are everywhere these days.
The ones writing poetry, composing music, even having surprisingly coherent conversations.
That's the one. Our listener sent over Ganguly's lecture, Large Language Models and Transformers, Perspectives from Physics, Neuroscience, and Theory.
Catchy.
Right, and dense. But to kick us off, Ganguli goes straight for something called scaling laws.
Sounds intimidating, like a law of physics, but for AI.
Exactly. So what are these laws all about?
Well, at their simplest, scaling laws tell us that as you pump more data into an AI model and increase its parameters, think billions of data points, trillions of connections.
Bigger is better, basically.
That's the general idea, yeah. The model's errors, the mistakes it makes, tend to go down.
So everyone's just making these models bigger and bigger.
It's a common approach, but Ganguli argues that simply scaling up is inefficient, maybe even unsustainable in the long run. Think about it, GPT-3, one of the biggest language models out there. It chews through data equivalent to 20,000 years of nonstop human reading.
20,000 years, even if I never slept again.
Exactly. So clearly our brains are doing something much more efficient than just mindlessly consuming data.
There's got to be more to it than that.
And that's Ganguly's point. He suggests it's not just the amount of data, but the structure of the data itself that might hold the key.
So, like how it's organized, what kinds of information are more common than others.
Precisely. He talks about power law distributions, where some features are far more common than others. Think about language. You've got tons of examples of everyday conversations online.
Way more than, say, ancient Sanskrit poetry.
Exactly. And Ganguly has found that if your training data follows this kind of power law distribution, the model's performance as you scale it up follows a similar pattern.
Interesting. So the data itself is shaping how these models learn and grow?
It's a two-way street. But if simply scaling up isn't the answer, what does Ganguly propose we do?
Yeah, if it's not just about throwing more data at the problem.
He suggests something called data pruning, basically being much more selective about the data we use to train these models.
So instead of a massive buffet, it's more like a carefully curated tasting menu.
I like that analogy. And his team has shown that this pruning, while still theoretical, can lead to exponential improvements in a model's ability to learn. They even propose the idea of a foundation data set.
A foundation data set.
Yeah, a carefully curated, non-redundant data set that could be used to train all sorts of models.
That's a pretty ambitious goal, creating this perfect foundation of knowledge.
It's a huge undertaking. And while they've had some success with image-based tasks, applying this to language models is a whole other beast. But this is where Ganguly's multidisciplinary approach comes in. He doesn't stop at data pruning. He dives into AI creativity, using examples like Stable Diffusion.
Stable Diffusion, those AI image generators.
Exactly. And he uses them to understand how these models can be so incredibly creative, even with limited experience.
You're talking about those images that look so real they could be photographs, but then there's something slightly off, surreal about them.
Exactly, like an astronaut riding a horse on the moon.
I mean, every time I see that image, it's just, how does a model even come up with that?
That's what Ganguly's trying to figure out. And one thing he highlights is that these models are successful because they don't perfectly memorize the data.
So it's their imperfections that make them creative.
In a way, yes. It's fascinating. There's a flexibility that lets them explore the unexpected.
That's kind of a beautiful thought. So how does he study this AI creativity?
He focuses on something called diffusion models. Imagine a picture slowly being corrupted by noise, becoming more and more random until it's just static. That's the forward process.
Okay, I'm picturing it.
Diffusion models learn to reverse this, to go from that random noise back to a structured image.
So it's like taking a completed jigsaw puzzle, scattering all the pieces, and then the model has to learn how to put it back together again.
Perfect analogy. Now here's where it gets interesting. If you train a diffusion model perfectly, it only reproduces the exact images it was trained on, no creativity.
A one-trick pony.
But by imposing constraints, preventing that perfect memorization, you start to see that spark of creativity emerge.
So you're saying constraints actually boost creativity.
Counterintuitive, right? But it speaks to a balance. Ganguly calls this exponential creativity with polynomial experience.
Catchy. What does that even mean?
Basically, with even a limited amount of training data, these models can generate a huge number of different outputs. That's the exponential creativity part.
Okay, I see.
But it's the constraints that unlock their true creative potential.
So we've got structure, chaos, memorization, forgetfulness. It's all playing a role here.
And Ganguly and his team are trying to decode the rules of this complex dance. One concept they're exploring is something called locality constraints. This is where the jigsaw puzzle analogy comes in handy again.
Okay, hit me with it.
Imagine each puzzle piece represents a small part of an image from the training data. Instead of memorizing the entire picture, the model learns these local patches and then pieces them together in new ways, guided by the puzzle's constraints.
So even if the final image is something completely new, it still makes sense because the pieces fit together in a coherent way.
Exactly. And the amazing part is that Ganguly's team is actually using this framework to predict the output of these models.
Wow, so they're treating this creative process, this seemingly magical thing, as a mathematical equation governed by local interactions and constraints.
Precisely. And that just scratches the surface. From here, Ganguly takes us into the world of in-context learning.
In-context learning, that's where it seems like these models are learning through osmosis, right?
Right.
Just absorbing information without any direct instruction.
Right. Like you could teach someone a new card game just by showing them a few rounds without explaining the rules. Ganguly gives the example of an LLM learning to pair scientists with their countries of origin.
Like Marie Curie, France.
Exactly. Show it a few examples, and it starts making accurate predictions for scientists it's never encountered before.
Okay, that is pretty impressive. But how do they even begin to figure out what's happening inside these models to make that possible?
Instead of trying to analyze a fully trained LLM, which would be incredibly
The
complex.
trillions of connections we talked about.
Exactly. They did something really clever. They focused on a simplified version of a transformer, a random transformer, at its initial state before any training has taken place.
So to understand these super advanced LLMs, they're looking at models that are basically blank slates.
Essentially, yes. And by analyzing how signals move through these random transformers, almost like tracing the flow of information, they can gain insights into the underlying architecture, the very foundation of learning.
It's like instead of trying to understand a finished building, they're studying the blueprint.
Precisely. And you know what's amazing? They found that by studying these random transformers, they could actually predict how well a model would perform after training just by analyzing its initial state.
That's wild, like predicting a student's success just by looking at their empty notebook at the beginning of the semester.
Right. It speaks to the power of looking at these systems from a different angle, bringing in tools and perspectives from physics to understand these complex AI systems.
So we've talked about scaling laws, data pruning, AI creativity, and now in-context learning. Ganguly's bringing in all these insights from physics, but there's one piece of the puzzle we haven't touched on yet, neuroscience. Where does that fit into all of this?
That's a great question. And it leads us to the final and perhaps most mind-blowing part of Ganguly's lecture, the intriguing connections between artificial intelligence and the human brain itself.
So we've talked about Ganguly's work on making these AI models more efficient, more creative, but where do our brains fit into all of this?
Well, this is where things get really meta. Ganguly points to some recent research using fMRI, brain imaging, and they're finding some interesting correlations between the activity patterns in LLMs and how our brains process language.
So we're seeing echoes of how we think reflected in these artificial systems.
It certainly got people talking. There was one study, they found that they could actually predict what was happening in people's brains as they were processing language just by looking at the activity patterns in an LLM and with a surprising degree of accuracy.
Wait, so by analyzing these artificial networks, we can get a glimpse into our own minds. Does that mean we're on the verge of creating AI that thinks just like us?
Hold on, let's not jump to any Matrix-like conclusions just yet. These findings are exciting, but correlation doesn't equal causation, right?
Just because two things happen at the same time doesn't mean one is causing the other.
Exactly. And Ganguly himself cautions against overinterpreting these results. He points out that these LLMs are incredibly complex. Remember those trillions of connections? That complexity could create misleading correlations. It's like finding shapes in the clouds. Sometimes a pattern is just a pattern.
So a healthy dose of scientific skepticism is still needed here.
Absolutely. LLMs might be powerful tools, but they're not about to replicate the full complexity of the human brain anytime soon.
Right, right. They're not about to wake up and start writing their own deep dive episodes.
Not yet, anyway. But I think that's one of the important takeaways from Ganguly's lecture, a sense of humility in the face of the unknown. We're still in the early days of AI. There's so much we don't know about how these models work, let alone how they compare to the human brain.
Humility, skepticism, and that drive to understand. Sounds like the making of a good scientist to me. But speaking of understanding, Ganguly's lecture throws a lot at us. Scaling laws, data pruning, AI creativity, in-context learning, insights from physics, and now these connections to neuroscience. Where does it all lead? What's the big picture here?
At its core, I think Ganguly's lecture is a call to action for the entire AI community. It's a call to move beyond this bigger is always better mentality and really try to develop a deeper, more fundamental understanding of how deep learning actually works.
So it's not just about building models that can write a decent poem or generate a cool image. It's about understanding how they're doing it.
Exactly. And that's what I find so compelling about Ganguly's work. He's not content to just build impressive systems. He wants to crack open the black box, unravel the mechanisms that make it all possible. He's challenging us all to be better scientists, to dig deeper, question our assumptions, and never stop exploring.
It makes you think about these LLMs differently. We started off talking about them as these massive data gobbling machines.
Right. Just force feeding them information and hoping for the best.
But Ganguly's lecture shows us it's so much more nuanced than that.
It's not just about brute force computation.
It's about data structure, randomness, all these things we haven't even begun to fully understand.
And that's what's so exciting. There's so much more to uncover. And Ganguly's approach, bringing in these different perspectives.
Physics, neuroscience. It's really refreshing.
It's like he's reminding us that we're still just scratching the surface of what's possible with AI.
And the real breakthroughs, the things that will really move the field forward, those are going to come from a deeper, more principled understanding of these models.
Not just building bigger and bigger systems, it's about unraveling those fundamental mysteries, the ones that underlie intelligence itself.
Whether we're talking about artificial intelligence or the kind we walk around with every day.
Exactly. It's about curiosity, exploration, pushing those boundaries of what we know.
Well said. And on that note, I think it's time to wrap up this deep dive into the mind-blowing world of Surya Ganguli and LLMs.
Time flies when you're exploring the frontiers of AI.
Huge thanks to our listener for sending us Ganguly's lecture. Really got us thinking.
Definitely one to revisit.
If you're as captivated by this as we were, we highly recommend checking out some of Ganguly's work. Links will be in the show notes.
And if you're hungry for more deep dives into cutting-edge research, hit that subscribe button wherever you get your podcasts.
We'll keep digging into the research so you don't have to.
Until next time, keep those minds curious.